The Instrumented Systems module is used for the design phase of the safety lifecycle. This is the module in which Instrumented Independent Protection Layers, or IPLs, like safety instrumented functions, interlocks, and alarms, are designed. These are the same IPLs identified in the LOPA module. However, in this module, users can see the specifications of each of these IPLs and how they are designed to work to achieve the required level of safety, also known as the safety integrity level. This video will cover how to use the Instrumented Systems module to create safety functions, link them to IPLs in the LOPA module, perform SIL calculations on Sifts, compile their safety requirement specifications, and how to form a cause and effect matrix which shows the action that will take place when a function has been activated. To access the Instrumented Systems module, click on the Module Selection drop-down in the title bar and select Instrumented Systems. Once there, you'll see the user dashboard, which shows the KPIs and reports for this particular module. You'll also see object tree and features. For the object tree, there are some objects that are unique to the Instrumented Systems module. In the object tree, you'll see objects that were created in the global module, the enterprise, the site, the unit, and equipment. And then you'll also see objects that are unique to Instrumented Systems. You'll see the 4 function types, alarms, BPCSs, the basic process control systems, Sifts, and interlocks as well. You'll also see your safety instrumented systems, which is made up of a collection or grouping of safety instrumented functions. We will talk about what each of these functions are made up of, as far as inputs and outputs, but first, let's go to the features. These are the same function types that we were referring to when we talk about IPLs in the LOPA module. So we're going to use this module to link the already existing functions to IPLs in the LOPA module through the Opa Function Sync. The purpose of the Opa Function Sync feature is to sync up IPLs that exist in the LOPA module with functions that exist in the Instrumented Systems module, and be able to take credit for those IPLs. This can be done in one of 2 ways. If the function does not already exist in the Instrumented Systems module, you can create a new function from a list of IPLs that would be generated, or you can sync to a selected function. Here's how it's done. Below, you can filter by site, by unit, by IPL type, and then IPL category. On the left side, you can see the IPLs that exist in the LOPA module and the corresponding functions that they can be synced to in the Instrumented Systems module. These are the functions that already exist in the object tree. In order to sync an IPL with a function, just select an IPL in the IPL list, select a corresponding function, and click Sync Function, or Sync to Selected Function. If there isn't a function that already exists in Instrumented Systems, just click Create New Function. Once the function and the IPL have been synced together, in looking at the LOPA module, this will show how the alarm is now synced to the IPL. The LOPA Function Sync feature can be used for IPLs of alarms, BPCSs, interlocks, and Sifts. So now that we have looked at how to link objects in the Instrumented Systems module with the LOPA IPLs, let's look at the details of these various functions, starting with SISs and Sifts, Safety Instrumented Systems and Safety Instrumented Functions. The Safety Instrumented System is located under the unit, and the most basic way to think about it is just a collection of Sifts and interlocks that protect against the same process or equipment. For a SIS, just like with any other object in the system, you'll see a basic registry or information tab that lays out the basic information about the system. You can also see if this has been linked to any of these functions, if they have been linked to an IPL in the LOPA module here. Now, with the sys and the sif objects, look for these double daggers. This tells you this information will go on to the safety requirement specification. And this is required as documentation to be kept for creation of these functions for auditing purposes. This is what the FSA will look for whenever you have an FSA auditor coming through. So in the end of all of this information, it culminates in a printout. It's a collection of various fields, or all the fields in this sys, all in one sheet. And so you can use this for your SRS, or Safety Requirement Specification, report. With a SIF, it's the same idea. Clicking on a SIF, once again, you'll see a SIF overview tab laying out basic information pertaining to the SIF, and then with each of these tabs, it describes more about that SIF. And once again, look for the double dagger fields for any information that is specifically required for SRS purposes. Because this is an overview video, we're not going to go into each of these tabs for your sys and your sif, but we will go into particular tabs and explain some of these in further detail. For example, your SilCalc Summary tab, Instrument Inputs, Instrument Outputs, and then dealing with your SilCalc, IO Sensitivity, PFD by type, and RF by type. So first we'll go into the Instrument Inputs and Instrument Output tabs. This tab will show the voting structure. This is your input group, your input voting group, along with its voting. It allows you to add any set points, and then below it will show your input that has been added. You can add further inputs, input voting groups, or input groups by clicking on any of these buttons below. The same goes with your instrument outputs. Here you can see your output groups with its voting, output voting group with its voting, and then the outputs that have been under this voting group. You have two outputs in this particular voting group. Now let's look at the object tree for a SIF to show what it looks like as well. Here you can see the voting. This is your input group, input voting group, and your input. This is the set point for your input. This is your logic solver associated with the SIF. And then this is the output group, output voting group, and outputs. This is the object tree view. Now looking at the input and output objects, first the input object. Here it allows you to see what type of input it is, whether it's a flow transmitter, or pressure, temperature transmitter, other. It allows you to select the general clean service class, or just the service class, and then additional information about that input. For the output, the same idea. It'll tell you what type of output it is, whether it's what type of valve it is, or solenoid. Once again, allows you to select the service class. And then additional information about that output, including testing. Now for both the inputs and the outputs, it also allows you to see which functions are using this input and output as well. And this is important because you can have the same transmitters or valves being used by multiple functions. Now the voting and the inputs and outputs must be consistent with the specifications for the SIF. So towards one of the last tabs for printout, once again, just as with the safety instrumented system, it lays out the safety requirement specification for the safety instrumented function. Now that we've discussed the design for the SIF, let's go over the SILCalc summary portion of the SIF. SLM has its own SIL calculation tool located on the SIF, on the SILCalc summary tab. This tab allows the user to look at what a SIF would look like from its inputs, voting, to its outputs. It also allows the user to calculate the risk reduction factor to determine the safety integrity level of the SIF. These calculations are determined by things like voting for the SIF, test coverage, proof test intervals, the common cause failures, and the failure rates for various inputs and outputs. The flexibility of this tool allows for multiple failure rates from different sources to be included in the calculation and ultimately compared in the end. Another benefit is that this SIL calculation tool uses the power of the SLM platform to be able to gather prior use or failure rate information from Operate Maintain module and use actual data in your SIL calculations. This data is valuable because this is gathered by the particular sites that are using this tool. And so basically we're using their own failure rate data to show them how safe their functions really are. So this area allows the user to play with the design of the SIF. It allows the user to play with the voting, failure rates, and other information that goes towards the SIL calculation without actually messing with any of the data that is recorded on the SRS. So now let's look at a more complex SIF and go over the design and layout of the SIL calculation tab. Remember, you can always collapse the accordion menu in order to provide yourself with more space. Whenever there is a lot of information on a particular tab and it's spread out, then it's helpful to have that closed. So now looking here, in the top portion, you can see the diagram for the SIF. This is your inputs all the way on the left, and going from the left to the right, you have your inputs, your input voting groups, input groups, a logic solver, the output group, output voting group, and your outputs. Now on the various voting group objects, it will display the voting between the objects that are a layer under it. So for example here, your inputs, they're 2 out of 3, and so 2 of these must trip. On the logic solver, we also have another layer of voting that allows 3 layers of voting overall. Over here you can see the dotted lines. This means that these objects are not included in the voting. This is beneficial for when you want to play with voting to see what happens with your risk reduction factor overall. This can also be used to display other portions or other functions, perhaps auxiliary functions, that are not directly a part of the SIF and its voting. And you can click on any one of these objects to be able to take you directly to the template for that object. Below, you're going to see a table that is used to show all the information that is used in your SIL calculation. There are 3 major sections in here that relate to the diagram above. So you have your input section, you have your logic solver section, and then you have your output section. Below, we're going to see the same thing. Here, we'll have your input section. Below that, you will have your output section, well, the logic solver section, and then the output section. Now, each of these fields, look at the information icon, and it'll give you additional information about what that field means. You can also refer to the study guide for additional information on how to use this tool and definitions for these fields as well. So each of these is the voting configuration for the various layers. And then over here, you have your inputs. Here, this is where you can associate the generic model with their PIU certificate, and then also have a custom failure rate data. Applying a PIU certificate with a generic model will take the information from that generic model object, like the failure rate data, and whatever failure rate data is included in that generic model, then it will be added to this particular area as well. So for example, only PIU information is on this particular generic model. Sometimes it could be other things like Exida, the more other outlets for calculations, and so on. Now pressing the edit button all the way in the top left portion allows you to edit any of these fields. The checkboxes is what causes you to select or unselect these particular objects for the voting that precedes it. All of this information will culminate in the numbers that you see at the bottom of the screen that compare all of the different failure rate sources that can be involved in this calculation. Now here, you'll see a custom failure rate data and prior use hours, and only the custom failure rate data is actually calculated because with the outputs, there isn't any information, as well as the logic solver, there isn't any information from the operate maintain module. So now that the total RRF has been calculated, we can see what this looks like in other tables and charts. This is where the PFD and RRF by type come into play, as well as IO sensitivity. Let's start with the PFD by type. The PFD by type will show the failure rate based off of what sources of failure rate data you have in a table format. So it will also show in a pie graph the areas of your greatest percentage of failure rates from your inputs, your outputs, and your logic solver. The RRF by type shows what your target risk reduction factor is determined by your LOPA, and then it shows you what you meet, or what this particular Sift meets. IO sensitivity will once again show your total risk reduction factor calculation, but then it gives you an additional tool to use. This is your Pfd Sensitivity Chart. So here you have your input test interval, input step, input failure rate source, and then the same for your outputs as well. So this allows you to calculate what the risk reduction factor will be based off a table that shows various intervals for your input and output testing. Clicking on Generate will result in a graph that shows all the information based off of the numbers we plugged in above. The various colors, or lines, are your input test intervals by years. The x-axis is your output test interval by years, and then your y-axis is your risk reduction factor. Below, we also have a table that shows what your risk reduction factor is based off of your input test interval and your output test interval. For example, if you chose your input test interval to be 5 years and then your output test interval to be 2 years, then you would have a risk reduction factor of 166 for this particular SIF. So this is a powerful tool because what this allows the user to do is determine what is the best test interval or the most ideal test interval for both your inputs and your outputs to achieve their goal. This allows them to not test as frequently, saving more money, while at the same time guaranteeing that they do have the amount of safety or the safety level that they would like. So once again, the other functions in instrumented systems are alarms, BPCSs, and interlocks. And remember, each of these can be linked to an IPL in the local module. So now that we've gone through the structure of a SIF dealing with inputs, outputs, and voting, it makes it easier to understand the structure for interlocks and alarms. For alarms, there are 2 tabs. The first will show basic information about the alarm. The second will show instrument inputs. And this will show all of the voting for the alarm as well as the input for that alarm. All of these fields that you see are the same as with the Sift because it is the voting objects and the input object, as well as the set point. Looking in the object tree, once again, it's the same structure that you saw for the Sift. The voting, inputs, and set points. For an interlock, it has the same basic structure as a Sift does. And clicking on the object will reveal the same type of basic information for an interlock that you would see on the initial function tab. However, this shows an instrument inputs tab and an instrument outputs tab. The other function is a BPCS, the basic process control system. Here, the structure has a controller, inputs and outputs, but no voting. The BPCS object, once again, has the same initial tab with the basic information for it, and then instruments inputs and outputs, but this time with no voting. Now, as all the other functions showed, you can also see the expected demand rate, max failed test rate, max failed to operate rate, and max spurious trip rate. These fields will be instrumental in populating or comparing Tier 3 metrics whenever we get to operate maintain. To create any one of these three functions, you click on the unit object, select Edit Tools, and select Add Alarm, Add BPCS, or Add Interlock. Once you've created all of your functions, you can take your Sifts and interlocks and with it build a cause and effect matrix. The cause and effect matrix is a child of the unit, so you go to the unit, select Edit Tools, Add Cause and Effect Matrix, type in a cause and effect matrix ID, and upon the creation of that cause and effect matrix, you'll see a cause and effect matrix tab and a setup tab. So since there has not been any setup done, we'll click on either setup screen or the setup tab, and that will take you to the setup tab. Here you'll see the cause and effect name, description, revisions, and then it will show functions included, inputs and outputs that were selected as well. So because we haven't selected any, there's nothing here. So in order to select the functions, inputs and outputs, you click on Manage Functions and Selected IOs. Then here it will show all of the interlocks and Sifts that are available in the unit. You can select the interlocks and Sifts that you would like to create the cause and effect matrix with, and click Next. And then it shows a list of inputs and outputs for this interlocks and Sifts. So you can select all or make a select amount. And afterwards it will show everything you selected in the Setup tab. Once you have set up all of this, if you go to the Cause and Effect Matrix tab, it will show your cause and effect matrix. Right, there's different sections to this cause and effect matrix. Your rows will show your functions, their descriptions, and any information dealing with the inputs. Your columns will show your outputs, their descriptions, and PNIDs. And where the two intersect, that's where you can mark your effects. In this portion, you can see the legend and any notes that you'd like to add. So we can add a couple of notes. Click Save, and these will be the notes that you will select whenever you are choosing an effect. So when we go down here, we can select Close, and let's say whatever note applies to that. And the same thing here. So this will allow you to choose between alarm, close, de-energize, energize, manual, not applicable, open, permissive, run start, and trip stop. You can use each of these or select each of these in your effect portion. You can also filter by the function that is shown. So if you only want to see interlocks, then you can select only interlocks, click out of it, and it will show just interlocks. If you only wish to see Sifts, just select Sifts. In order to get all functions back, click on All Functions, and it will return you. You can see for normal, shutdown, and startup, you can see what the effects are in each of these cases for these functions. Once your cause and effect matrix has been set up, you can print it or export it to Excel. One of the major advantages of using SLM for the cause and effect matrix is that it automatically creates your matrix for you. You just have to select the functions once they're already created in the Instrumented Systems module. So now that we've visited the idea of a cause and effect matrix, and we've also explored looking at how to create the various functions and what they look like structurally, we can look at some of the reports that this module has to offer as well. For each of the function types, you have reports that you can print out or see in a tabular format. There's a protection category report for each of the functions that have been created in Instrumented Systems. So for alarms, BPCSs, Sifts, and interlocks. You'll see that type of report. Next, you'll see the function type summary. And this report will show all of your various function types, the number of them, by site. If you wish to filter down further for a specific unit, then you can do that as well. The generic Sift templates report is used to design Sifts with specific generic model types for their instruments, inputs and outputs, and then be able to create that particular Sift based on the desired voting. So here this will show for inputs, you can see 1 out of 1, 1 out of 2, 2 out of 2, and 2 out of 3 voting, and then for outputs across the top, you can see 1 out of 1, 1 out of 2, and it'll show 2 out of 2, and so on. This also shows your RRF for a particular voting configuration and test interval. Clicking on this will actually create a SIF with that design. The other type of report is an SRS printout, a safety requirement specification for your SISs and SIFs. So upon finishing discussing reports, this will conclude all the topics for this particular video for instrumented systems. In this video, we covered an overview for how to link functions with IPLs in the LOPA module. We covered how to view SISs and SIFs and the various functions and how to create the structure for them. We also talked about the importance of SIL calculations and how those are calculated, along with various reports and information that you can get from that. And then we also talked about how to create cause and effect matrices. So once these various functions have been created down to the inputs and output levels, this will feed into going into the operate maintain module, where we will build out devices, assign generic models to those devices for failure rate purposes, and allow us to gather the data upon failures and successes for each of the tests, demands, maintenance events, and so forth. And so this is what all this information is going towards, is the operations and maintenance portion of the safety lifecycle.